Good afternoon. I'm Les Barani. I'm making this video in order to demonstrate a simple and efficient method of deriving the Laplacian in spherical coordinates. Unlike prevailing methods, this one greatly minimizes the need for memorization or detailed sketching and requires only basic undergraduate math skills. As we shall see, it also works for the divergence and curl operators. In a previous video, I demonstrated a method of deriving the gradient in spherical coordinates using a trick of linear algebra that minimized computation. I'll leave a link for that video in the description, but the gist is that the unit vectors and partial derivatives needed form matrices that happen to be invertible by inspection. Since that method produced a gradient so easily, I'm going to use the gradient as my point of departure in order to compute the spherical Laplacian. This time, I'll show how complex numbers simplify this computation. Looking at the formula in Cartesian coordinates, we're tempted to regard this as being the square of the gradient, which it happens to be in Cartesian coordinates, but the actual definition of the Laplacian is the divergence of the gradient, so this is unfortunately not the right answer. What complicates matters is that the operators in the factor on the left have to act on the unit vectors in the factor on the right. So we have to use the product rule in taking the specified derivatives, which includes taking derivatives of the unit vectors. Popular methods complete this process using 3D visualization, combined with advanced mathematics like differential geometry or Riemannian geometry, but I'm going to show a simple algebraic way. First, I'll write this operation as a matrix outer product, which is just an operation that forms all possible products between the elements of the vector on the left and the elements of the vector on the right, which is what the divergence of the gradient requires. Executing the outer product gives a rather daunting looking object, but it has a great bookkeeping advantage in showing everything in one place, and in particular, makes clear where the product rule introduces the unit vector complication. So I'm going to start with the unit vector derivatives, but rather than follow the usual tactic of making complicated sketches in perspective and trying to visualize how various quantities change as a result of varying coordinates, I'm going to use an unorthodox trick. So looking at plane polar coordinates, hopefully familiar from Physics 101, we know how to represent a radius vector, represented here by the Greek letter rho, and how to find its corresponding unit vector. When this radius vector changes, say by rotating through an angle phi, its unit vector also rotates, unlike what happens in Cartesian coordinates where they're always fixed. We notice that there's a phi unit vector that also rotates, staying perpendicular to the rho unit vector. Common convention assigns a positive vector to counterclockwise rotation. You could view the phi unit vector as the rho unit vector transformed by rotation. But you can save a lot of time by viewing the same system in the complex plane. Here, we can take advantage of the fact that multiplying any complex number by I causes a vector representing that number to rotate pi over 2 radians, or 90 degrees, counterclockwise. This, of course, is easy to see by multiplying 1 or I and so forth by I. Now, according to Euler's relation, the plane polar radius vector can be expressed as a complex exponential. And we can see, by using this familiar trigonometric identity, that the magnitude of the exponential factor is always 1. So a vector has its magnitude expressed by a coefficient. And therefore, the unit rho vector is equal to this, and the unit phi vector must be equal to the same thing multiplied by I, since it's perpendicular. And that is exactly the same thing that we get by taking the derivative with respect to phi of the rho vector. We get the phi vector. And if we differentiate a second time, namely differentiate the phi vector, then we get the negative rho vector, and that tells us how the unit phi vector, phi hat, changes as the vector rotates. But now, Suppose we borrow this representation from polar coordinates and use it in spherical geometry. In other words, instead of writing the spherical radius vector like this, we write it like this, and likewise for the unit vector. Then we can write the unit vector of the spherical polar angle like this, it being the derivative with respect to theta of the unit radius vector. And lo and behold, we can differentiate these expressions with respect to phi and also with respect to theta to get the other unit vectors derivatives needed. And remember, these are partial derivatives, so coordinates not appearing in each derivative remain fixed and act as constants. Finally, it's easy to see that no unit vectors change magnitude or direction as they travel along the radius vector, so those derivatives are all zero. The rho coordinate, like the x and y coordinates, acquires a factor of sine theta going to spherical coordinates. So we have the 9 partial derivatives of the unit vectors, which we need, and we can get back to the business of calculating the divergence of the gradient from the matrix we found previously. Now what we get by executing the product rule derivatives looks a little bit frightening. But if you look closely, there is a great simplification about to happen, and most elements are zero. One nice thing about matrices is that addition is very straightforward, and we can actually split this matrix into two, the right containing all the second derivatives and the left containing the unit vector derivatives. And the elements in the one on the right all have dot products, which are either 1 or 0, so the mixed partial derivatives all vanish, leaving only 3 terms. On the left, we can insert all the unit vector derivatives we found, and either through vanishing derivatives or dot products, we collapse this matrix to 3 terms. Here I've gone over to subscript notation for the derivatives. So the answer we get is boxed in blue. You will often see this equation represented in the form which is boxed in green, but if you carry out the indicated derivatives, you will see that they are equivalent. Earlier I mentioned that the divergence and curl can be computed with the same method. As you can see, although they are defined differently, the computation follows the same pattern. The key to this method was in replacing the unit vector for the radius vector in spherical coordinates with a representation that was derived through complex analysis. And this allowed us to easily compute all the unit vector derivatives, and therefore a straightforward divergence of the gradient could be calculated simply by applying the divergence operator to the gradient vector. And thank you very much for watching. Please comment, like, or subscribe, and stay tuned for more. Bye for now.